Okay, let's do example number 7 here. We have a 4 kilogram box, and that's M1, and a 6 kilogram box, M2, that are being pushed by a 30 Newton pull force, pushed by a pull force. Okay, well, it should probably be a push force. Okay, and there is a force of friction of 5 newtons on M1 and a 10 Newton frictional force on M2. Draw both free body diagrams and find the acceleration of the blocks and find the internal forces. Okay, so let's draw a free body diagram. So this will be, how about we do this M1? So this is the FBD of M1, and it's 4 kilograms. And it has a frictional force of 5 newtons. And it has a force of gravity of, well, the force of gravity on this object, well, I guess we don't need to do that, it's not hanging. So we'll just ignore the force of gravity. And it has a 5 Newton push, 5 Newton frictional force. And on this one, we free body diagram. This is M2, and this is 6 kilograms. And it has a frictional force of 10 newtons acting on it. Okay, so M1, it's sitting on a surface, therefore it has a normal force. It's near the surface of the Earth. It has a force of gravity. It has a push force, so we draw it as a pull. F push. It looks like rush with the arrow there. Push. And then we're pushing on M1, and M1 pushes on M2, and that's the action. And the reaction is M2 pushes back on M1. There's that seems like the resistance force to stop it from being pushed, and the inertia of M2. Okay, so the reaction force is pushing on M1. Okay, and that's the force pushing back. What do we call it? I kind of like calling it action-reaction. So force, action, reaction, pushing that way. And now there's going to be an action force of far on here. And that's going to be like the ropes we just finished doing, but they're internal still like the ropes, but they're going to be pushing instead of pulling like ropes do. And they will cancel out when we look at the system. So this one has a normal force and a force of gravity. Okay, there's no push force acting on it because the push force is touching M1, not M2. But there is a frictional force on both of them, and the frictional force drags back, and that's the frictional force on this guy, and there's a frictional force on this guy. Looks good. That's it. There's no more other arrows to draw on our free body diagram. So let's look at the system. So when we look at the system, we have to ignore the internal forces, which is the push and pull. If there are ropes, the tensions in between the blocks we'd ignore. And let's look at the mass of the system first. Mass of the system is 10 kilograms. And the forces, the sum of the forces on the system. Let's take a look at that. It's the direction of motion is in this direction. Whoops. And the normal forces cancel out the force of gravity. That's why it stays on the surface. They don't fly off the surface. And that's the direction. So we have a push force in that direction and 2 frictional forces in the opposite. We ignore the far because they push and pull same amount, opposite, cancel each other out. So we have the push minus the force of friction of object 1 minus the force of friction of object 2. The push force here is 30 newtons minus the two frictional forces. The number 1 is 5 newtons and number 2 is 10 newtons. So the total force there is, the sum of all the forces is 15 newtons. Newton's second law, sum of the forces is equal to F net, which equals MA. And that's 15 newtons is equal to the mass, 10 kilograms, times A. And we get an acceleration of, and that looks like 15 divided by 10, 1.5 meters per second squared. And we'll box that off. Whoops. That's one of the answers that it asked for. Okay. So let's start off here and let's look at M1. And I guess we're going to try to find the internal force now, which is the action-reaction force. So M1, the sum of the forces equals F net, which equals M1, MA. So the sum of the forces, just take a look, it's that direction. So it's the push minus the FAR minus the force of friction on this block. So it's the push, the force of the push, minus the action-reaction, minus the force of friction equals MA. And the push here is 30 newtons, minus FAR, minus the force of friction, minus 5, is equal to MA, 4 kilograms, times the acceleration of 1.5 meters per second squared. Okay, so that is 30 minus 5. So that's the action-reaction is going to equal 30 minus the 5 minus, and that's 6. And so that looks like 19. So we get FAR is equal to 19 newtons. And I'll not scroll off so we can see all the work that's going on. Not scroll off, and here I scroll. Let's set that there. And in fact, I can just select all this, and you can do it too on your page if you want. Okay, it's probably not an electronic page that you're doing it on. Move it on over and get yourself some extra room. And now let's do this in green. The sum of the forces is equal to F net, which equals MA. And we're going to check on this one, and we're going to solve for FAR again. We have it, but we're going to see if it's 19 on here. So again, this is the direction of motion. So FAR minus the force of friction is our net force. So FAR minus the force of friction is equal to MA. And so FAR minus 10 newtons is going to equal to 6 times 1.5 meters per second squared. That's our acceleration. 6 is our kilograms, and mass in kilograms. And if you just do the math quickly, you will see that the FAR is going to be 10 plus the 9. 1.5 times 6 is 9. So that's again 19 newtons. That's our check. It checks off. Yay! And how about the smiley face? You have a lot more room to put it on the page. I decided not to use the whole page. Woo! Tried to fit it all in this one little area, but at least I did it for the video. Thank you very much. Hope you understand what's going on here, and that's example number 7.